Hey y'all, in this lesson we'll be looking at the basics of polynomials. So we will be using some things like leading coefficients, leading terms, degree, and table of values to sketch a polynomial, the graph of a polynomial, and then also use that information to write a polynomial in factored form. Before we get into all of that, I want to define a polynomial for you so that you know what that is. Basically, a polynomial is an equation with multiple terms, if I were to put it in simple words. But mathematically, what it looks like is this, which might seem a little intimidating, but it's not as bad as it seems. So each of these a values are actually just coefficients. And each of these x components are the variable terms. And the exponents on them are written in descending order. So n is the highest exponent. N minus 1 is the one below that. N minus 2 is the one below that. And you go all the way down until you end up with the constant. So the constant has no x term because x to the 0 is just 1. The degree of the polynomial is going to tell us some important information. It is the highest exponent, and it tells us how many zeros there are. So when we were looking at quadratics and we had the highest exponent was a 2, that meant that we had at most 2 zeros or 2 x-intercepts. The leading term of the polynomial is the term that contains the highest exponent. And the leading coefficient is, it's not rocket science, it's the coefficient of the leading term. So just that leading term can tell us some important information that will help us sketch our graph. In this polynomial, it's kind of gone down on the second line, but it's 4x to the third minus 6x to the fifth plus 7x squared minus 2x plus 1. We can write this in standard form. I'm going to call it f of x. I didn't name it, but we'll just pretend. And that's where you start with the highest exponent. That's a negative. Sorry, the negative's right here. It just didn't go down. And then work your way down. 4x to the third, 7x squared minus 2x plus 1. And this term is the leading term. And what it tells us is the, degree, which is the exponent on it, and the leading coefficient is going to give us not only information about the end behavior of our graph, but also will help us as we write polynomials in factored form. The degree of the polynomial determines the largest possible number of zeros, which is another name for x-intercepts that there are. Now, it gives us the largest possible number. So there may not be, in a quadratic, the largest possible number of zeros is 2, but when we graph it, we may only see that there's 1. So it doesn't necessarily give us exactly how many, but it gives us the largest possible number. And then the sign of the coefficient determines whether the function opens up or down, or sometimes the the function goes in opposite directions. So it's going to tell you, what it looks like, basically. The factor theorem states that if k is a zero of a function, then x minus k is a factor of the function. And this relates back to, if you remember from quadratic functions, if we had a quadratic function in standard form, and then we factored it in factored form, then we use the zero product principle to, split those factors up and solve each one. In this case, we added R1. In this case, we added R2. And so what this is saying up here, instead of r, it's using k, but it's just a variable, so it means the same thing. If r or k is a 0, is a root, is an x-intercept, then we can work our way backwards and say x minus r or x minus k is a factor of the polynomial. So that is all that this means, and that's called the factor theorem. And we will use that in our polynomials when we find some of our zeros or roots. We will use that to write it in factored form. We know that for quadratics, we can factor that because we've already learned it. But as our polynomials get bigger and bigger and bigger, those degrees get higher and higher and higher, it's really hard to it's really hard to factor them, if not impossible to factor them just by looking at it. So we can simplify it down to, okay, well, let's find the roots or the zeros. And if we can find the roots or the zeros, then we can use this theorem to write it in factored form. I have an example here. This one is actually a quadratic, which we've already looked at before, so this should be kind of a review, but I'm going to use this simple example to show you how to apply it to polynomials. In this case, I have the table of values already completed. In cases like your homework or something, that may not already be done. And to do that, you can use your graphing calculator. This app is free. It's called Graph Calc. I'm going to go to y equals. I'm going to type in the function. I'm actually going to write it in standard form. 3x squared plus 6x minus 9. 3x squared minus 6. Nope. Sorry. Plus 6x minus 9. And then I'm going to go to the table. And you can see where I got these values. So you can do that. If you want to do it by hand, you would just evaluate the function at each of those x values, and you would end up with the corresponding y values. But that's not the point of the lesson. So the leading term of this function is the term with the highest exponent. The coefficient on that term is a positive 3, which indicates that this graph is going to be opening up because it's positive, so it's going to be a U-shaped graph. The constant term is the term with no variable, and this is going to be your y-intercept. The degree of the term is the highest exponent, which is 2. This is an even degree, and I'll show you later when we graph it what that means, what it indicates for the graph or the function. And then the zeros of the function, we know that there are at most 2. We know that zeros are x-intercepts. And for an x-intercept, the y value is what? Do you remember? 0. Let's go to the table and locate the places where the y value is 0. There's 2 places. One is right here, and one is right here. So my zeros are x equals -3 and x equals 1. And there won't be any more than that because I know that with a degree of 2, there are at most 2 zeros. This information is telling us a lot about our function. And so that's why it's important to list out that information as you're working on problems. Now we know by the factor theorem that if these are zeros, then we can get them on the same side, and now we have factors. On this one, we would subtract 1. But for factored form, you'll notice in standard form that I have a leading coefficient of 3. Well, that 3 doesn't show up here. So what we're going to do is write that coefficient as our a value and then our factors out beside it. And you might be wondering, how in the world did she get here from here? How are those the same? They're not the same, but they are. This is standard form, this is factored form. So they are equal, they just look different. If I were to go over here and have the original function and factor it using my factoring skills from quadratics, I would pull out that 3, and then I would find factors of -3 that equaled 2, and there it is. So this can be factored using factoring techniques from quadratics. But the reason why I wanted to show it to you this way was because when we move further into polynomials with higher degrees, you're not going to be able to do that so easily. If you have x to the 5th power, that's going to be real hard to factor. And so if you can find the zeros, then you can write it in factored form using those zeros and the leading coefficient. Now I'm going to sketch the graph. When it says to sketch the graph, it doesn't have to be exact. You just want the general shape of it. In this case, we can actually pretty much get the graph almost completely on the coordinate plane. So we're going to be pretty close. But as you get into higher degree polynomials, you may not so much be able to get it all in the graph. You're going to get some really high y values or really low y values, and you can't see them on the graph, but we can get the general idea. If I note important information from my table, like the x-intercepts, the y-intercept, and even in this case a vertex, I can get a really good idea of what this looks like. So I'm going to go to -3, that's an x-intercept, +1, that's a y-intercept. Nope, I'm sorry, x-intercept. 0, -9 is the y-intercept. Sorry about that. And then the vertex is a little bit off the graph, but I can estimate where that is. And then my coefficient tells me, the degree tells me it's an even degree. And the coefficient is positive, which tells me it's going to be opening up. This is a parabola. This is a quadratic. So it's going to be a U-shaped graph opening up. And it is a little bit skinny because of the coefficient, the 3. So I'm going to sketch it. I'm actually going to use a wider pen because it's easier to graph that way. And it would look like that as a sketch. So this was an even degree, opens up, and that's going to give me information about my end behavior. End behavior is referring to what's happening to the ends. These indicate ends in a graph, and we want to talk about what they're doing. As x is getting smaller, my y values are going up. They're getting higher and higher and higher. So when you write that down, you say, as x is approaching -infinity, getting smaller, my y values are approaching +infinity. They're getting bigger. And then on the other side of the graph, as x approaches +infinity, getting bigger, my y values are also getting bigger. So it's also approaching +infinity. So for an even degree function that opens up, each endpoint goes up. So just kind of pin that in your mind. Both, whoops, spelled that wrong. Endpoints go in the same direction. So we'll just keep that in our minds. And now we're going to go to an odd degree function so I can show you the difference. So that is all at once. We have sketched a graph based on very important information. So if you're doing a homework problem and it asks you to sketch a graph, I would recommend going through some of these steps to get that information that you need to write it. If it's asking you for factored form, this is what you're going for. So it's really not too bad. It looks like a really long problem, but it's really not that bad. I'm going to skip down to example 4 down here because two things. It's an odd degree polynomial, and we're going to find something kind of tricky with the x-intercepts, which will lead into the next lesson that I'm going to do in a different video. I want to write this in standard form first. This is j of x, and I want you to pause it and write it in standard form, then come back and check it. Hopefully you did 3x to the third plus 14x squared minus 7x minus 10. The leading term is 3x to the third, leading coefficient is 3, constant is negative 10, degree is 3. So I went a little bit fast, but you should be able to see that just from this and this, which will also come into play in the next thing that I go over. This is so exciting. I love polynomials. The leading coefficient is positive, which is going to tell us something about the in behaviors. And also the degree is 3, which is giving us several pieces of information. It's telling us the largest possible number of zeros, and it's telling us about in behavior. This is an odd degree, and it also will have at most 3 x-intercepts. And that's why I'm wanting you to list these out, because it's telling you information. Remember, this constant is the y-intercept. So we already have some pertinent information to help us figure out what this graph looks like. Because we're going to see from the table that sometimes your values are so big or so small that it goes off the graph and you can't really tell what's going on. But we can use the information that we have to get a general idea of the picture to help us sketch the graph. So I have a blank table of values here. I want you to pause the video and fill out the table. You can either do it by hand or using the calculator. You are going to end up with some pretty big numbers because of the x to the third. X to the third means x times x times x. And so if x is 5, for example, 5 times 5 times 5 is really big. So yes, you will end up with some big numbers. Anyway, go ahead and pause it, fill out the table, and come back. Hopefully, if you did it in the calculator, you typed in 3x. If you're looking for the raised to the third button, you're going to have to use the caret function, which in this calculator is above the division symbol. And you can see it raises it to the third. We're going to do 3. And my cursor is still in the exponent, so I'm going to hit over to get out of that. Then plus 14x squared minus 7x minus 10. Table. And now I'm going to fill out my table. I've got a 0. Yay! I'm going to highlight that because that's important. 50, 56, 36, 8, negative 10, 0. Yay! 56. I'm going to highlight that. And I'm also going to highlight, whoops, that's not what I meant to do. The y-intercept. I'm going to label these. This is an x-intercept, this is an x-intercept, and this is a y-intercept. Remember, for an x-intercept, the y value is 0, and so that's how I knew that they were important. Now, when we try to plot these points on our coordinate plane, obviously these values are way off the graph. So we're just going to kind of get a general idea of what it looks like. I do have 2 zeros from the table at -5 and 1. So those factors would be x plus 5, x minus 1. But this function is x to the third. So I'm missing a factor. Because right now I have x times x, which is x squared. That means that there's one here that I'm not seeing. So I'm just going to kind of leave it like that for now. In the next lesson, which is in the next video, I'll actually show you how to find it exactly. But for now, we're going to leave it like that. In this example for this particular lesson, we're just going to estimate where we think it might be. And you can estimate by looking at the table or the graph. I will show you both, but I'm going to start with the graph. So to draw this, we've got x-intercepts at -5, +1, a y-intercept at -10, and I have one other point that can fit on my graph at -1, 8. Now you might be looking at this and going, what is that shape? It's not a circle, it's not an oval. And so we need a little bit more information to figure out where we're drawing. If you go back and you look at your table of values, we can see that the, let me pull this up. Negative values, negative x values, those y values are really, really, really small. -1000 is way down there. So if I were to kind of sketch an idea of that behavior, for negative x values, my y values are way down there. And then my next point goes up to here. And now I need to figure out what's happening in that region with -4, -3, -2. That is in my table. And that's kind of way up here, way off the graph. So I'm just going to sketch here. We're going up, 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 up. It goes way up there, and then it's going to drop back down to there. And then it goes down to my next point here. And then back up here. And if you look at the table of values again, as x gets bigger, the y values get really, really big. So this is kind of a rough sketch of what's happening. Let me make it a little bit bigger so you can kind of see it better. This goes way up, then it drops back down, goes through there, goes back up, and hopefully from that, we can see what's happening here. And we can see that it does have 3 x-intercepts. One of them is kind of in a decimal area. It's a rational 0. So 2 of them we saw from the table, and the reason why we couldn't see the third one is because it's a decimal. Now you can go in and change your table settings to have decimals. And so you can mess with that and keep changing your decimal like sizes, the number of decimals basically. I'm not going to show you that in this lesson because it's a whole other thing, but you can do that and you can narrow down what it is using your table of values. But we're not going to go into that. For now, we're just going to kind of estimate where that is. And we can see that that is pretty much going to be in between -1 and 0. So and we know that because it starts up high and then it drops down to the next point. So it crosses through the x-axis in this region. Now, if I go to the table of values and I look at -1 and 0 and note the corresponding y values, we can see that we went from a positive y value and dropped down to a negative y value. And that's going to indicate that it had to cross through the x-axis to get there. So there is another x-intercept between -1 and 0. And we would go on here, this is j of x, I think, and write this. The coefficient was a 3. Then we have x plus 5, x minus 1, and then we have this third factor that we know has to be a decimal, basically, or a fraction. And in the next lesson, we'll actually find exactly what that is. But for now, we're just going to leave it like that. I know that's kind of like, if you're like me, you're like, oh, I really need to know what that is. But we will figure it out, I promise. Don't worry. But we can say that we know with certainty that the third x-intercept is in between -1 and 0, because the sign on the y values changed between x equals -1 and x equals 0, indicating that it had to drop through the x-axis. This is called the intermediate value theorem. So if you're asked about the intermediate value theorem, that's what it's saying. You're locating that rational x-intercept by seeing that, the y values changed, and that means that there has to be an x value, an x-intercept between them. Then the end behavior, we can see that as x approaches -infinity, so as x gets smaller, our y values also got really small. And if you're having trouble seeing that from the graph, you can look at the table of values and easily see that from that table. Look at those y values. As x gets smaller and smaller and smaller, y also gets really, really small. And then if I go bigger on x, what happens to the y values? They're also getting really, really big, really fast. And that indicates our end behavior. As x approaches positive infinity, gets really, really big, y also approaches positive infinity. So as x gets bigger, y is getting bigger. As x gets smaller, y is getting smaller. So we have an odd degree polynomial, and my endpoints are opposite. And so I want to write this down because this is important. For odd degree, the end points are opposite. And this was a positive coefficient, the 3. And that means that we started low and ended high. So overall, it's going, not really, but up. If we were to go from here to here, it's going up because it's positive. So you could draw a little picture like that to kind of show what's happening. So odd degree, positive coefficient, my writing got kind of weird down there, but odd degree, positive coefficient means that the endpoints are opposite and we start low and end high. That means that if we had had a negative coefficient, we would have started high and ended low, still going opposite because still odd degree. And that's so cool. There's, never mind, rabbit trail. But you will see that these are going in opposite directions. That indicates an odd degree. And then in the even degree polynomial that we had up here, the endpoints were going in the same direction. So anytime you have an even degree, even means 2, 4, 6, 8, 10, so on, obviously, then your endpoints are going, or in behavior are going in the same direction. So if it's positive, they're both going up. And if it's negative, they're both going down, even degree. Odd degree, if it's positive, it ends up. If it's negative, it ends down. Hopefully you'll do more examples in the homework and kind of see how that comes into play. But I did want to point that out before moving on. Now, I mentioned that we couldn't really tell exactly where that third x-intercept was, especially from the table. But we can't just leave a question mark. That's not finished. And this leads me into the next thing called the rational value theorem, or rational zero theorem. Let me see, hold on. Rational zero theorem. This basically helps us figure out the possible rational zeros that could be that third x-intercept that we don't know. And so if we can list out the possibilities, then we can test those possibilities to see which one works. Now, we're not going to learn how to test them in this lesson. We will learn to test them in the next lesson. But for this one, we're just practicing listing them out. Because before you can figure out what the last one is, it will be nice to help narrow that down. There are an infinite number of rational numbers. So you could never figure it out just by guessing and checking. But we could narrow down those values using this theorem. And the theorem states that you take the constant over the leading coefficient, P over Q, and 10 is negative, but for this particular thing, I'm just going to leave the negative off because it doesn't really necessarily make a difference in the next step. What you're going to do is you're going to list the possible factors of each value, P and Q. 1 times 10, 2 times 5, 1 times 14, 2 times 7. And this is going to set up your possibilities. So we have several different combinations going on here. 1 over 1, 1 over 2, 1 over 7, 1 over 14, 2 over 1, 2 over 2, 2 over 7, and so on. So we're going to write all of those out. And we do, since there is a negative here, we do want to consider the positive and the negative possibilities. And we have positive or negative 1 as a possibility, positive or negative 1/2, 1/7, 1/14. Then you go to the 2's, 2 over 1. 2 over 2 is just 1, so I'm not going to write that again. 2 over 7. 2 over 14 is 1/7, so I'm not going to write that again. 5 over 1, 5 over 2, 5 over 7, 5 over 14. And the last one, 10 over 1. 10 over 2 is 5. 10 over 7. And then 10 over 14 is 5/7, so I don't have to write that again. We got a lot of possibilities. So we know that, I think this was the same function up here. Yeah, we know that -5 and +1 are already zeros. So we just need one more. And the possibilities are these values. And what we would do is we go through and check every single value, which is quite a process, but not impossible, kind of fun. And we know that, what was it? +1 and -5 were already 2 of our x-intercepts. And so we would test all the other values to find that last one. It's not as hard as it sounds. And this one is like, there's a lot of possibilities there, but hopefully you end up with something like the next example. Let's write it in standard form. 3x squared plus 6x minus 9. You take the constant over the leading coefficient. 9 over 3. List out the factors. 1 times 9, 3 times 3, 1 times 3. And then list out your combinations. 1 over 1, 1 over 3, 3 over 1. 3 over 3 is just 1. 9 over 1, 9 over 3 is just 3. So these would be your possible rational zeros. Now, luckily on this one, we already found from the very first example that we could see those from the table of values. So this one, we found that the two zeros were -3 and 1, which if you go back here to our possibilities, you can see that -3 and 1 are in that list. And so let's pretend like maybe we didn't have the table of values or we didn't have the graph and we had no idea how to factor. then we could list out these possibilities, and then we could test each possibility, and we would find that 2 of the zeros are in the list. And we're going to use that in higher degree polynomials where maybe all the zeros are rational and we can't see it from the table or we can't tell from the graph. Then we can use these possibilities, and then we can use long division or synthetic division to help us find the exact x-intercepts that we're looking for. We will do that in the next lesson, not this one. So we will learn that, but not in this one. That's all I have for sketching polynomials, though. If you have any questions or need any help, please let me know, and I'd be happy to be there for you. Hope you enjoyed it, and I'll see you in the next one.